Continuing from our previous lecture on Introduction to OLS Regression, I'm going to talk about a little bit regarding the assumptions of OLS regression. More specifically, what are the mathematical and statistical assumptions which are running behind OLS regression. So first and foremost, the primary assumption is that the independent variable and the dependent variable or have a linear relationship between each other. So this is the first and foremost of all assumptions in OLS. So as we mentioned before, OLS captures the linear relationship in the form of a line segment formula, i.e. y is equal to mx plus c, or y is equal to beta naught plus beta 1 x plus the error term or the residue. So underlying this is the base assumption that x and y, the independent variable and the dependent variable, have some sort of a linear relationship. So OLS regression will not work where there is no linear relationship or there is a non-linear relationship. For example, if there's a logarithmic relationship or an exponential relationship or a sinusoidal relationship, in that case OLS regression will not be able to capture the relationship appropriately. It can only work when there's a linear relationship between IV and DV throughout the ranges in which we are building the model. Second assumption is that independent variables are independent of each other. So till now we've only covered OLS regression using one independent variable. So I'll come back to assumption number 2 when we start off with the multiple linear regression. So as a quick background, in multiple linear regressions, we have multiple independent variables against one dependent variable. So right now we are building a model where y is equal to mx plus c. But supposing we have two independent variables x1 and x2, in that case the formula becomes y is equal to m1 x1 plus m2 x2 plus c, where m1 and m2 are the slope estimates against the two different independent variables x1 and x2. So this particular assumption follows that the two or more independent variables that we are building in our model are actually independent of each other, i.e. they don't have any relationship with each other. So I'll come back to assumption number 2 when we start off with the multiple linear regression later on. And the third assumption is regarding the errors or the residuals in our model. So as I explained before, in the regression formula we have an error term. So where we say yi is equal to beta naught plus beta 1 xi plus the error term. So this error term is the error in our regression, or is the unexplained variance which our model will not be able to explain. So over here, as you can see, the scatter diagram between x and y. So while we fit in the line of the least error, there will still be error. So uh, we will never be able to capture the relationship perfectly unless x and y are perfect functions of each other. In most cases, primarily in all cases in the real world, that will not be the case. We will always have an error in our regression for modeling. So regarding the error, there are some assumptions on this error term. The assumption is that the error term is normally distributed around the estimated mean value of y for any value of x. The mean error of or residual is 0. So what this essentially means is that the mean value of the residuals is always 0, i.e. the positive residuals and the negative residuals will always cancel out each other. So if you remember, we calculated the y hat in the regression that we had built by hand, and this is the actual y and this is the error that we got. So error over here is the difference between y and y hat. So one of the assumptions of the error term is that the total sum of the error or positive errors will always be cancelled out by the negative errors. So if I sum up all the error terms, I'll get a sum of 0. And this is an assumption of regression which will always hold true if we build the model correctly. So the mean error or the residual is 0, and the distribution of this error term around the mean is supposed to follow a normal distribution. So we can actually plot or build a histogram around this, and we will see that the errors or the residuals are always normally distributed around the mean, which is 0. So this is an assumption, and once in some cases this can actually be violated, and we need to be careful around that. The third assumption on the errors is that it has a constant variance or homoscedasticity. This is a little difficult concept to wrap your head around. So I'm going to try and uh, visually plot it out for you. For example, let's go back to the smooth draw program, and let's say we are building a regression model on a scatter diagram again of x and y. So I build my axis over here. I've got x-axis pertaining to the variable x. I've got y-axis pertaining to the variable y. And let's build a scatter diagram over here. So as you can see, x and y appear to have a very strong linear relationship with each other. As x increases, y continues to increase, and let's assume that this is the line which minimizes the error between the minimizes the error between y and y hat. So assuming that this is our regression model, and y is equal, or y hat is equal to beta naught plus beta 1x plus c, and y is equal to y hat plus the error term. Now in each case, the error term is the difference between the predicted value of y and the actual value of y, or the difference between the dots and this line of best fit. So for each of these points, the distance they are from the line in terms of only the y-axis. So we are only looking at the y distance, we are not looking at the x distance. So that becomes the error term that we have. And we know from the assumptions of errors that the positive errors will cancel out with the negative errors, and I'll have a mean error of 0. However, what it also says is that the errors will be IID. So this is a new term which we're going to talk about. This means identically and independently distributed. So IID means independent and identically distributed, and that would follow that they have a constant variance. So what this essentially means is that for any value of x, supposing I have a value, I'm testing for a value of x1 over here, x2 over here, and let's say x3 over here. So if I look at the value for x, for x at x1, the observed values of y range from this point till this point, and the mean value of y is obviously the value at the point where x intersects with the line. So if I look at the errors around y, for if I build the formula what y hat is function of x1. So given x1, I get a y hat, but the actual value of y is ranging from the negative dot here till the positive dot over here. So I get a range of values for y for a given x centered around the line. For again, for if I look at x2, so I get a range of values for y when I'm holding x2 constant. And again, if I look at x3, I get a range of values for y if I hold x3 constant. So what IID essentially tells me is that it doesn't matter what the values of x are. So it can range from x1 to x2 to x3 till xn. At for any given value of x, the error term in where the values of y will be constantly distributed. So if I assume that this is one variable over here, so I get values of y ranging from, let's say, uh, yj till yk over here. So I have a range of values for y for a given x over here. So this range of values will have a mean, and that mean will be centered around y hat for x1, and the errors will be positive and negative, so they will follow some kind of a distribution. So if I look at the errors alone, they will be normally distributed around a mean of 0. So they will have a normal distribution and a mean of 0 and a certain standard deviation in it. Now if I look at the distribution of errors around here, also around the mean, they will also be normally distributed around a mean of 0, because positive and negative errors will cancel out each other, and they will have a standard deviation. And if I look at the errors over here as well, so here as well they will be normally distributed around a mean of 0, and positive errors will cancel out the negative errors. So I get three different distribution of errors for values of x at x1, x2 and x3. Now the assumption tells us that the distribution of errors for any given value of x is IID. By IID means they are independent and identically distributed. So we'll take the identically distributed part first. What it means is identically distributed means that the distribution of errors for x1 is exactly the same as the distribution for errors for x2, which is exactly the same as the errors for distribution in x3, i.e. all of these distributions are coming from the same underlying population. So they are different samples coming in from the same population. So they are virtually the same distribution. The mean will be 0 and they will have a constant variance across. So the variance of the distribution at this point, the variance or sigma of the errors at this point is going to be the same as the sigma of errors at this point, and it's going to be the same as the sigma of error at this point. The mean is going to be the 0 for all three distributions as it is. So what we are essentially saying is that the errors will follow a identical distribution no matter the value of x or the value of y that we are tracking based on the regression formula. They are going to be identically distributed. By independent, what it means is that knowing the value of the error term, I cannot make any assumption on the value of x or y. They are independent of each other. For example, I only know that the error for the nth term or the nth observation in my dataset, the error is, let's say, -10. Looking at the value of this error, I cannot make any prediction or error that what is the value of y or what is the value of x, because there's no information in it. Therefore, the errors are independent of each other. And knowing the error at one term, I cannot predict the error of any other term as well. So if I know the error at this point is 5, I can't say what will be the error around the observations around here as well. So errors have no information in them. They are independent of each other. So knowing the error of let's say x2 will not give me any insight into the errors of x3, and similarly it will not give me any insight into the errors around x1. So there is no information in the errors. Knowing errors gives me no particular edge, so that is why they're independent of each other. So this is where the term independent and identically distributed comes from. What it essentially means is the errors follow a constant variance around the line of best fit. So there will not be a case where the errors are suddenly large or suddenly small. So I'll give you an example where this violation gets violated. So let's have a look at, I'll just draw out another diagram. So let's have a look at this diagram over here. And I'm going to create a scatter diagram as well. So that's too big. Let's make it smaller. Yeah, that's more like it. So just let me make this. And let's look at this scatter diagram. And let's. So I've purposely made this scatter diagram looking like some sort of a dumbbell, if you might say, with a large mass at the center rather than the ends. And let's look at, let's look at the line of best fit. And let's say we apply OLS over here and we get a line of best fit like this. Now, what you will observe is that the errors on this end, right? If I look at the errors for, let's say, x at x1, this is x2 and this is x3. They are just uh, three observations that I picked up from the data set. If I look at the value of x at x1, I see that the errors range in somewhere over here. Positive errors are still cancelling out the negative errors, so the mean is 0, but the standard error of errors is a certain value, and this might follow a normal distribution as well. Let's look at x2. At value equal to x2, I see that the errors have a large variance amongst them. So even positive and negative errors are cancelling out each other. Even this may be following a normal distribution, but I'll see that the distribution will have a larger standard deviation as compared to at x1. I look at x3 again. Again, I see the positive and negative errors will cancel out each other, so the mean error is still 0. But I see the standard deviation of these errors is small. So what we see at different points in time, different values of x1, x2, and x3, even though the means are same, the standard deviations of the errors are different. In this case, they are not identically distributed because they at different points of value of x, we have different standard deviations in the error term. So we see small variance in the errors over here, a large variance here, and again a small variance here. So in this case, there is not constant variance. So these distributions are not identical to each other. And if I know that the variance over here, if I make an error over here, let's say the error over here is large, let's say this value is 20 and the maximum error here is 5, the maximum error here is 5. If I know the error at 20, error is 20, then I can actually make a guess that if the error is 20, it's quite likely the value of x is ranging between this range over here and y is ranging between this range over here. So I can start making guesses regarding the value of x and y based on the error term. So that means also the errors are not independent, right? And if errors are large, then I can be sure that the errors around this area will also be large. And the error, if the error is small, then it's likely to be uh, surrounded by small errors. So I can start making guesses around the error term as well. Therefore, they're not independent of each other. So this is what we mean by when I contrast IID versus non-IID. OLS assumes that we have constant variance in the errors around our regression line. So if I have a data set which is looking something like this, so that is a violation of OLS. So one should not build a linear regression model when we have data like this, and that's a supposed violation of OLS. However, just because it's a violation, you may not want to drop OLS directly. So it's better that you know about the violation and do something about it rather than not knowing about it. So there are ways of handling heteroskedasticity in our data set. So this is an example of heteroskedasticity. Hetero means different, and therefore in this case we have the variance is different at different points of the value of x and y. So henceforth it's known as heteroskedasticity. Homoscedasticity assumes that the variance is constant. So homoscedasticity is a assumption of the OLS regression. We require homoscedasticity in our error terms. If there is heteroscedasticity, that's actually a violation. And it was always a good idea to generate the correlation between the dependent variables and residuals. So as mentioned earlier, residuals are the random error term, so there should be no information in the residuals. If the residuals are actually correlated, and if I look at this example, I see that the error terms increases. So if I only analyze the data set at this point in time, I will see large errors tend towards large values of y. So there might be some correlation over here. In this case, there's a correlation between the error term and the value of y. Because larger errors tend towards larger values of y. So in this case, there's correlation, and that's again a violation. So I need to check for correlation as well. If the correlation between dependent variable and residuals is coming out close to 0, that's a good thing. And lastly, we can also check for a histogram of residuals to check for normality and presence of outliers. So again, since we look at the sum of squared errors and we are minimizing the squared errors, as shown in correlation, an outlier in our data set can actually have a outsized impact on our regression model. So let's look at a hypothetical example. What does an outlier do? So let's see, I have my data set. Sorry. So again, I'll just make a scatter diagram. Let's say this is my scatter diagram, and the line of best fit in this case is something which goes like this, right? But I have one observation which is lying over here. So this observation is lying over here, and when I look at the error this observation makes, so if I look at this error, this is an outsized error, and the impact of this error actually gets gets increased by an order of magnitude because we are looking at error square. So what the OLS will automatically try to do is it will try to minimize the total error by making the line go somewhere over here. So instead of getting this line 1, which is the correct regression line, what OLS will do is it will build a linear regression model which goes something like this. So in this case, the error term, instead of being this whole mod order of magnitude, it becomes something like this. The error is only this much. So it will reduce the error based on this point, and it will inflate the errors over here and give me a line, this line 2, and the formula for this line, which is beta no beta 0 plus beta 1x, will get fitted onto my data set. So instead of getting a regression line which was supposed to look like L1, I'll get the regression line which is L2 because of the presence of a single outlier. If I remove this outlier from the data set, I will immediately revert back to L1. But presence of a single outlier completely changes my regression model. And this is uh, while this is not a violation of the assumptions, because this is just how OLS works, it will give me a poor, or it will give me a bad performing model, and I would want to avoid using outliers. So again, by doing some sort of residual analysis, we can actually check for presence of outliers as well in our data set. So these were the assumptions of OLS regression, and I'm quickly going to go do a recap again. The first assumption is that the dependent variable and the independent variable have a linear relationship. If there are multiple independent variables, the assumption is all of the independent variables have a linear relationship with the dependent variable. Second is collinearity, that the independent variables are actually independent from each other. So we will come back to this is an assumption later on when we do multiple linear regression. Third is regarding the errors of the residuals. The assumptions regarding residuals are that they are normally distributed with a mean of 0, and they have a constant variance or homoscedasticity of the residuals, i.e. the residuals have a constant variance throughout the term irrespective of the value of x or y the model is predicting at that point in time. So they should be independent or identically distributed throughout the regression model. So these are the three assumptions of OLS regression. So this is an example of where homoscedasticity and heteroscedasticity can come into play. So if you look at these two examples, these two scatter diagrams. So if I build a model of best fit over here, the line is going to run something like this. And throughout my regression model, you can see that the variance and errors over here or here or here are actually going to be constant. So that there is no the variance around the line is supposedly constant throughout the regression line. But if I look at this example over here, let's say OLS builds a regression line something like this. So I can see the errors over here are small, but as the value of x starts to increase, the errors start to become larger, larger and larger. So therefore the variance of the errors at different points of value of x is actually getting more and more large. So while the mean of the error terms is 0 throughout, because positive and negative errors are cancelling out each other, the standard error of the residuals starts to rise based on the value of x or y, and that means they are not IID, and that's a violation of OLS. So OLS requires homoscedasticity in the residuals, and heteroskedasticity. This is an example of heteroskedasticity, and that's actually a violation of the rules of ordinary least squares. Right. So this was the assumptions of OLS regression. So what I'm not going to do is I'm going to show you how to build or do a simple procreg procedure on SAS for ordinary least squares. We're going to do it for only one variable, so one dependent variable and one independent variable, and I'll see you in that next lecture for this.